Hello, everybody. I'm Seyma Mercimek, PhD student in the context of European Horizon 2020 ITN Network, Astrochemical Origin in INAF Archetri Observatory and University of Florence. Today, I will talk about the first molecular detection of the protostellar disk of VLA 1623W and its streamers imaged by an ALMA Arch program FAUST. So as we know that stars form from cores, taking these stages from class 0 to 1 and then later class 2 in the protoplanetary disk. And then later it forms our solar system. So in this evolutionary stage, the general thought might be the stars are forming in quite isolated environment as a single star, but statistics from the observations tell completely different story. Here on the right, you see a multiple frequency as a function of time. The fraction here is computing taking the old stars by removing those which are singular systems. So if you go to class 0 stage, which is the youngest protostars, the multiplicity fraction is very high. It can go up to 70%. When time evolves more towards the main sequence, the fraction goes down, but still remains very high, around 40–30%. So here you see some large programs, mostly from ALMA, and other facilities to target different stages and instruments. Here you can see Kepler, Gaia that can give us opportunity to get this information, statistic information. So here the message is that the most of young stars are likely a part of multiple systems. So as we see for class 0 stage, the being multiplicity is a norm rather than being an exception. This lowering multiple frequency with time may be due to the dynamical interaction in the system in terms of theory, but recent high angular resolution observations also reveal the presence of accretion streamers here in the protostellar system. For instance, in a class 0 protostar spanning size up to 10,000 AU, meaning that the material here is coming from its surrounding envelope to feed the disk, protostar disk. So on the right, the sketch shows the classical dance core, and these streamers coexist at different evolutionary stages of a protoplanetary disk. So here it starts with a prestellar core, which is under gravitationally collapsing. And the next stage shows the classical picture of the dance core feeding the disk and with additional multiple here streamers. And later on here, once most of surrounding envelope is gone, some late accretion events would be driven by the streamers. In the early stage, as we know that disk is still accreting now material from its envelope through the accretion streamers. So that means that instead of spherical collapse that we think of in our basic understanding for star formation, we may need to assume that streamers funneling in the material could be more common as we start seeing these streamers in all later stages, in more evolved stage here, for instance, in class 1 and later class 1-2 protoplanetary disk in the HTAU case. So in these streamers, also are presenting in more evolved here systems and in the protoplanetary disk, then they might generate the initial over-densities necessary to generate rings in the disk before the planet formation process is in the full swing. And even later stage here on the right, when planet formation is ongoing, a streamer could deposit material in an inner disk as required to explain the difference between different meteorites, for instance. So summarily, such accretion streamers are observed also very more evolved stage, not only in class 1 or class 0 stage. And this may play a crucial role in the determining the final mass, the disk mass, and chemical composition. So to understand this multiplicity evolution and interaction in the system kinematically with these possible streamers, an ALMA large program, FAUST, are going to show several systems with those streamers soon. So mainly the aim of this large program is to reveal and quantify the variety of chemical composition of the envelope disk system at scales of 50 AU, where planets are expected to form towards the listed class 0 and class 1 protostars here. And now I'm working on VLA2023 class 0 protostellar cluster to understand kinematics and the system interaction through the streamers. Here on the right, you see an image from a previous FAUST paper related to this source. So VLA1623 consists of four protostars. So here you see very close two protostars, A1 and A2. They are surrounded by a circumstellar disk, and these class 0 protostars next to these protostars, there is another class 0 protostars, which is source B. These three protostars surrounded by a circumbinary envelope, and there is another source which is more evolved stage, class 1 stage. Source W is located at least 1030 AU distance from the main system. So here the all molecular works related to this source have been focused on only the system A and B. So with the FAUST, with the high angular resolution and sensitivity observation, now we want to focus more on the source W. So the no molecular study focusing on source W makes it interesting, obviously. So our study, which is now under revision right now, focused on C18O molecular emission towards the disk of source W at 50 AU scale, and also elongated structures aligned along the north and the south direction. Here you can see, which we see there are streamer also feeding the disk of source W. Additionally, with band 6 dust continuum analysis, we also report fitting parameters as well as disposition angle, inclination angle, and dust mass for source W. So here you see moment 1 map of C18O towards the disk of source W. So you can clearly see blue shifted and red shifted lobes separately. Also here I show a dust continuum map from band 6, and then you see with star the position of the star, the center. Assuming Keplerian rotation, also we derive a dynamical mass is around 0.5 solar mass, which consistent of being a low mass star formation. And one of the most important, also interesting feature from the channel maps we saw towards the disk of source W, actually the systemic velocity of source W is about 2 km/s different than the systemic velocity of the whole system. And please keep this information in mind that we will use it later. So what is important of the molecular detection of nearly age-on disk, class 1 disk? So shortly, And the importance, simply to say, previous theoretical studies show that the disk middle plane with orange, which has dust grains and frozen molecules that we are not able to observe with a molecular emission. And there is a molecular layer with the green that is warmer with respect to the middle plane, so that we can observe with high angular resolution observations in the molecular emission. So, but at least still it's very challenging to observe complex organic molecules in the disk in a face-on located sources. So instead, we need to go to a high inclined protoplanetary disk to map this vertical stratified structure to able to see this warm molecular layer. So here I show you an example from this high inclined protoplanetary disk. Again, another ALMA work showed that with the high inclined class 1 disk, some molecular emission, CO, CS, and H2CO. And for the first time, they also mapped methanol, which is mother of complex organic molecules, in a class 1 protoplanetary disk. And in the large scale, C18O emission is also showing very important feature that I talk about that in the beginning of my talk. Streamers. We detect 3 streamers, one in the northern part, which we called northern arc, partially also overlaps with the outflow cavity driven by source A. This is CS emission from previous work. And in the south direction, we have 2 streamers, again connecting source W with system A and B. So what all streamers means? At the end, we suggested 2 scenarios for the interaction between system A and B and source W. Actually, the difference, special difference between source W and A and B is about 1,300 AU difference. And also difference on the systemic velocity is about 2 km per second. Can say that maybe source W has been ejected from the system A and B in the beginning of the formation of multiple system, or it can be a flyby. So the close encounter that occurs during the ejection of one of the members of a multiple stellar system has a similar kind of dynamical effect as that of stellar flyby. In the case of a flyby here, if the outer perturber, which in our case source W, follows a propagate orbit near the disk of disk envelope of system A and B, this could kind of lead to formation of streamers like ones observed in C18O emission here. Interestingly, here in the map also we detect a spiral arm in this southern direction to system A and B, which is diametrically opposite with respect to the northern spiral arm here, which connect AB with source W, as the similar picture, for example, of another flyby example from UX theory from Menard 2020. They show the similar behavior, both both from observations and models. Of course, if this flyby case takes place, this would indicate that source W and system A and B interacted recently, forming these diametrical opposite spiral arms during this encounter. Additional kinematic constraints are needed in order to test this stellar encounter scenario of this protostellar cluster. Also, much higher angular resolution observations with force and CO SO and SIO needed to understand if there's a shock region close to streamer, and then affect this feeding activity towards source, towards the disk of source W. And with this, I want to thank you to listen me. If you have any question, I am here to answer.